Next up, I want to apply the Lagrange remainder form to the functions log and arctan that we've studied, whose Taylor polynomials we've studied in the beginning. So let's see what we can do with the Lagrange remainder form from this. And I will formulate this as the theorem because this is kind of important formulas, these two. Namely, we can show that indeed polynomials approximate the functions very well in a certain area. Namely, we can say that log of 1 plus x, this is really the limit of the Taylor polynomial, so to say, namely the series. Series n from 1 to infinity, minus 1 to the n minus 1 divided by n times x to the n. And now this holds for all x and not everywhere, but between 0 and 1, both included. So this means that it's, if there would be some finite end at the sum here, this would be a Taylor polynomial. So this just means this is the limit of the Taylor polynomials here, which is now a power series. So we can locally kind of write this in this area. We can write this as a power series. And in particular, we get a nice little formula that I just want to point out. If we insert x equal to 1, this is kind of the last point on the right-hand side that we can insert, we get the formula for the logarithm of 2. And now this is simply always 1, so we simply get sum from n equal to 1 to infinity of minus 1 to the n minus 1 divided by n. And if you take a close look at it, up to multiplying this with minus 1, this is the alternating harmonic series that we've seen in the chapter about series. There we've seen that there was an example of a series which converges but not converges absolutely, and does not converge, which does not converge absolutely. But here we see that, so we couldn't compute the value. We could just show the convergence by the Leibniz test. And yeah, we know that the absolute value here, they get the harmonic series, which is divergent, so that was the argument. But here we now can compute this, just using Taylor's theorem. So as a byproduct of this, we get a formula, and it turns out this surprisingly adds up to log 2, which is highly non-obvious, of course. Who could have guessed this just from this formula? Okay, secondly, we get the same for the arctan. We also get the representation as a series, also as a limit of the polynomials. This is the same as the sum from 0 to infinity, minus 1 to the n, divided by 2n plus 1 of x to the 2n plus 1. And this time this holds for all x between minus 1 and 1. So again, it's just too much to ask to have the whole function be a power series, because this is obviously not always the case. But here we can just describe this locally, so kind of in this sufficiently small interval, we can describe it like this. And I will show that this also has a nice consequence, namely we will derive from this, and I will tell you in the proof why this follows, a formula for pi. Namely, it follows that pi is 4 times the sum from 0 to infinity minus 1 to the n divided by 2n plus 1. So this means this is the same as 4 times 1 minus 1/3 plus 1/5 minus 1/7, and so on. So this is an interesting formula for pi. Yeah, so this formula is a bit like the typical YouTuber. It's very nice to look at, but really can't do much, so it's not really useful. Because this is kind of a formula which kind of where you can just compute pi and approximate pi by just maybe computing 1,000 terms of this formula. But it turns out that this formula actually converges quite slowly, and there are better expressions with which you can approach pi much faster, but it's just a nice, beautiful formula. Okay, so to prove this, we will use the remainder form. And in part A, this is quite simple. So again, we have the function, and now this time we study it on the interval 0 to 1. F of x is log of 1 plus x. And we now put Rn of x to be, again, the difference of f of x minus Tn f of x. And we want to show, and this is what we need to do, that the formula, that the sequence r to the Rn of x, n in n, that this sequence converges to 0 for all x between 0 and 1. Okay, how to do this? Okay, now we can use just the Lagrange remainder form by Theorem 442 for all. Remember we have, the Taylor formula with respect to 0. Taylor polynomials with respect to 0, of course. This is what we did before in the previous example, yeah. So by Theorem 442, for all x between 0 and 1, there exists some psi. Now, where I just formulate this is between 0 and 1. This position doesn't matter at this point. With the property that the remainder of x is then given as this by this derivative expression. And so we have Rn of x is f n plus first derivative of psi divided by n plus 1 factorial x to the n plus 1. This is Lagrange remainder form. Now we want to estimate this a bit. And now we want to show that this goes to 0, and it suffices to show that the absolute value goes to 0. This is this trick that we've used before many times. So this is bounded by 0. And so by the squeeze theorem, we just have to show that if we put absolute value around here, that this expression here goes to 0. Now, this is first of all just by using the standard computational rules for the absolute value. The absolute value of this here divided by n plus 1 factorial, and now x to the n plus 1. And since the absolute value of x is smaller than 1, we can just estimate this from above by 1. And so the whole thing here is, so recall, we have seen above, sorry, let me just put this in here, that fn of x is n minus 1 factorial divided by 1 plus x to the n. And now, oh sorry, I forgot the minus 1 to the n minus 1. So, but this minus 1 doesn't matter in this case. And so we get that this is smaller than or equal to, and now we insert this formula at that point. So we have n minus 1, here it's n, so we have to shift in degree by 1. So we get, for this fn plus 1 of psi, this is n factorial divided by 1 plus psi to the n plus 1 divided by n plus 1 factorial. And now this is just simply smaller than or equal to 1, so this doesn't need to be considered. So we again see that the factorials cancel each other out almost, so we can cancel out this, and this is n plus 1 times n factorial, so there's not that much remaining. So all that's remaining is 1 divided by n plus 1 times the absolute value of 1 plus psi to the n plus 1. And now since psi is between 0 and 1, this means that this here is between 1 and 2, so this particularly means that this here is bigger than or equal to 1. So again, we can estimate this from above by simply 1 over n plus 1, since this is making it smaller. So we've shown that 0 is smaller than or equal to Rn of x, is smaller than or equal to 1 over n plus 1, and this implies by the squeeze theorem, since this obviously goes to 0, that the limit of this here goes to 0, and so we can again forget about the absolute value. So this goes to 0 for all x between 0 and 1. But this shows, just by definition of Rn, that f of x is the limit as n goes to infinity of Tn f of x at 0. And this is, of course, just the limit n to infinity of the sum k from 1 to n, minus 1 to the k minus 1 over k x to the k. And this is, of course, just the limit of the partial sums. Just by definition, this is the series, the sum k, n from 1 to infinity, minus 1 to the n minus 1 over n, x to the n for all x between 0 and 1. And this is what we wanted to show. So this is the example of the logarithm. So for the arctangent function, this shows the formula, and I've already said how this follows. This is just the case of x equal to 1, so there's no need to prove this additionally. For the arctan, there's a similar computation. I will just put this in the lecture notes, basically, because let me just say this is in the lecture notes. And the argument is precisely the same. We take the difference of the function and the Taylor polynomial, so this remainder term Rn of x, and kind of do some little computations, nothing all too weird, nothing too special, to show that this is bounded by, this is kind of squeezed in between 0 and something going to 0. And by the same argument, we get the same property here. Same argument shows that arctan x is the limit of n going to 0, tn arctan of x at 0 for all x between -1 and 1. So the only thing that needs to be clarified now, or that I will clarify now, is where this expression for pi comes from. Now, so for the second part here, we have seen in that was sheet 8, exercise 3, that that was the exercise where you had to compute the values of sine and cosine for some special points. We have seen that the sine of pi over 4 is the same as the cosine of pi over 4. So by definition of the tangent, this is the sine divided by the cosine. So this means the tangent of pi over 4 is equal to 1. Okay, but since the arctangent is just the inverse, this means that pi over 4 is arctan of 1. And of course, this gives then the formula for pi by simply saying that pi is then 4 times the arctan of 1. And by the series formula that we just have proven, if you take a look at this, this is just this expression for x equal to 1, which holds here, 1 is included. So this is the same as 4 times sum going from n equal to 0 to infinity, minus 1 to n divided by 2n plus 1. And this is what we wanted to show. So in this way, just advise you to take a look at this computation. I've done all the explicit details in the lecture notes. So you do precisely the same method, and you just need to find some estimate. And again, by the Lagrange remainder form, the key is then by the Lagrange remainder form that you can really find some expression here so that the derivative comes into it, so but you get some explicit number which is coincides with this, and then you can do computations. And so you need bounds for the derivatives essentially to get results like this. Okay, now as the next thing, so one more thing I wanted to mention. Let me just squeeze this in here. Remark 445. Actually, part A of the previous theorem, so the logarithm formula, so of theorem 444, holds for more x, namely for x between -1 and 1, with -1 not included but 1 included. But we can just not prove this at this point. We need some additional techniques. I cannot prove this with the methods so far. So this, if you find it in a textbook or something, this might be for these x as well, but we can't prove this right now. Okay, let me now erase, and then we go back to local extrema. We now return to local extrema of differentiable functions, and it turns out that with higher derivatives, we can say a lot more than before. Theorem 446. So this contains sufficient criteria for local extrema. Namely, we want a function on an open interval. We have some point in I. We have n in n at these two. And we want that f from I to c to be n times differentiable. So we further assume that the nth derivative as a function from I to c is continuous. This is, for example, automatically the case if it's n plus 1 times differentiable, because this implies that fn is differentiable. Differentiable functions are continuous, so this is the most common situation that we consider. Okay, so that this is continuous, and we assume the following. The f prime of A is equal to 0, which is the necessary criterion by Fermat's theorem to be a local extremum. And we assume that more derivatives are vanishing, that the second derivative vanishes, and so on. And the n minus first derivative are vanishing. So these are all vanishing, and that the nth one is non-vanishing. So the interesting thing is kind of the first non-vanishing derivative. Okay, then we know that it's possibly a local extremum, but now we can say a bit more. Namely, if this n, so the first non-vanishing derivative at A, is an odd number, then f does not have a local extremum. Then we can really definitely say it's not a local extremum. A local extremum in A. Now if n is even, then we get that it is indeed a local extremum. B, if n is even, now we have to distinguish if it's a minimum or a maximum, and this can be done by the sign of the derivative. If n of A is negative, if fn of A is negative, then f has a local maximum. In A, and if n is even and the nth derivative is positive, then it's a local minimum. Then f has a local minimum in A. Okay. I don't know about you, but when I went to high school, we basically had we only considered the case of the second derivative. So we had, you have functions and you compute that the first derivative is 0 in some point, and then you see what, if the second derivative is positive or negative, and if the second derivative was 0, we basically try to exclude this case and only discussed vaguely what to do in this situation. So I guess this is not done in high school, but again, I'm older than you, so that was when I went to high school, so shortly after World War II. But I don't know if you saw this in high school in this general way, but I guess not, because it really, in a general situation, it requires Taylor. So how do we use Taylor's theorem in this case? So first of all, I first do the general things that are done for all three cases, and then we treat the three cases individually. So fn of A is non-zero, and we assume that fn is continuous. Then, it was basically some exercise we did once, that since it's continuous and this is non-zero, there is a neighborhood of this A where the nth derivative is non-zero on the whole neighborhood because of continuity. So it follows there exists some delta bigger than 0 with fn of x not equal to 0 for all x in A minus delta, A plus delta. So intersected with the interval, of course. Intersected with I, sorry. So for all of these x. But since the interval is open, since I open, we can assume without loss of generality, because we could just shrink delta and make it small enough, that A minus delta, A plus delta is completely contained in I, because you can always find such a delta which is that small, and then we have a second delta here, and we can just take the smaller one of the two, and this then has the nice properties. So this only makes it a bit simpler. Now, if we take a look at Taylor, we know that locally near A, we can approximate f by the Taylor polynomials at A. And since the point is here that the derivatives here are vanishing up to the n minus first, but this means that in the Taylor polynomials, the n minus 1 first summons, they just have to vanish because the coefficients are 0. So by assumption, not the first, only the 0th one remains actually. So by assumption, Tn minus 1 of f at x in A, this is simply f of A, because all the other summands involve the derivatives of A, which are non-vanishing. So this holds for all x in A minus delta, A plus delta. Hence, so by theorem, I mean, okay, this holds for even more x, so for every, this holds for all x, but we just need this for x in this interval. So by theorem 442, so by the Lagrange remainder form, for each x in A minus delta, A plus delta, there exists some xi between A and x. And this xi for us is only relevant that it's also in A minus delta, A plus delta, with, sorry for the cut, I made another computational mistake. There exists some xi such that f of x is the n minus first Taylor polynomial, which in our case is just f of A, plus fn at xi divided by n factorial times x minus a to the power of n. Okay, and this I reformulate just by bringing f of a to the other side. This is f of x minus f of a is equal to fn of xi divided by n factorial x minus a to the n. Okay, now, this is now the crucial part, and this is where we start distinguishing the three cases. If we take a look at this left-hand side, if a was a local minimum, this would mean that for all x sufficiently close to a, f of x would be bigger than or equal to, which then means, to f of a, which then would mean that the left-hand side of this equation here is non-negative. In the same way, if f of a is a local maximum, then all the values of f would be smaller than the one of f of a close to a, so this would mean that this side would be non-positive. So it depends what happens. And in the same way, if this would be sometimes positive, sometimes negative, this would mean this can't be a local extremum if it's kind of happening arbitrarily close. And so now we have a nice expression for this. This is a very simple expression that we can study. This is just some really simple polynomial. And so we can derive from here, from the signs of this expression here, if it's a local minimum, a local maximum, or neither. So let's start with the three cases. First of all, if n is odd, then we know that x minus a to the power of n, this is positive if x is bigger than a, and negative if x is smaller than a. So this is sometimes positive, sometimes negative, so no matter which sign this one has, this whole right-hand side will kind of arbitrarily close to a, we will always find positive and negative values. So it means that the left-hand side, f of x minus f of a, takes both positive and negative values, arbitrarily close, and this means formally in any neighborhood, so with respect to the domain I, in any I neighborhood of A, and this means that f of A is not a local extremum because we have both points which are smaller and bigger in every neighborhood. So this means f of A is neither a local maximum nor a local minimum of f. Okay, so for part B, the same thing, the same approach, but this time the sign issue is a different one. So now, if we have an even number, so in part B, that's in part B and C we have n is even. An even power is always non-negative. So and if the base of the power here is non-zero, it's definitely positive. So here we know that here x minus a to the power of n is always bigger than or equal to 0 for all x in a minus delta, a plus delta. So the sign of the right-hand side only depends on the side of this one, because this is also non-negative. And so if this is negative, the right-hand side will be negative. If this is positive, the right-hand side will be positive for all x. And then we have our equations. So in part B, where we assume that the nth derivative of a of psi, no, sorry, one little argument missing. So this holds, and since fn of a is negative and fn of x is non-zero for all x in this interval, it follows that, just by continuity, that f of n is negative everywhere in this interval. Because if there would be positive values by the intermediate value theorem, there would have to be a point where the function is 0. So since yeah, this is again from the continuity of fn, and fn of x. This holds, and so hereby, since f of n is continuous, let's do it like this. It particularly follows that f of n of x is smaller than 0 for all x in this interval. Whoops, sorry for squeezing again. So if we take a look at this expression here, so let's give this, let's call this star. So here it follows from, since so non-negative, non-negative, negative, so it follows that from the expression star, f of x minus f of a is smaller than or equal to 0 for all x in a minus delta, a plus delta. And this means, of course, that f of x is smaller than or equal to f of a for all x in a minus delta, a plus delta. And this is the definition of a local maximum. F has a local maximum in A. And part C is just the same argument, so I won't do this again. There's simply the other, basically reverse all the inequalities, because there we get that, this expression here is positive, and so the same argument shows that this is bigger than or equal to 0, and we can proceed in the same way to get the minimum here. So this really clarifies our classification of local extrema of differentiable functions. Okay, after erasing, I will give you one example. We want to compute the local extrema of an example, namely the local extrema, extrema of the function f going from R to R. F of x is x to the power of 3 times e to the minus 2x. Okay, first of all, we can see x to the 3 is differentiable, the exponential function is differentiable, so this is all composed of differentiable functions. So f is differentiable, and we compute the derivative. This is now by the product rule. So this is the first factor, this is the second factor, and we use the product. So f prime of x is, okay, derivative of the first factor times the second, so 3x squared times e to the minus x, plus first factor, x to the 3, times the derivative of the second factor, and this is by the chain rule. We get that differential of x with x itself times the inner derivative, which is here just minus 2. So we get minus 2 times the original function, like this. And this, of course, can be summarized by 3x squared minus x, minus 2x3 e to the minus 2x, and for our purposes it's convenient to write this as x squared times 3x minus 2, 2x minus 3, other way around, 2x minus 3 times e to the minus 2x. Okay, now by Fermat's theorem, the local extrema are zeros of the derivative. So by Fermat's theorem, the only possible local extrema, so we don't know yet if they are, so it's just local extremum points, to be precise. The extremum points are the zeros of this function here, and if you take a look at this, we know that e, the exponential function, is never 0, so it's only the zeros of this. And of course the product is 0 if one of the factors is 0, so either x squared is 0, which means that x is 0, and the fact that this is 0, and this is precisely the case if x is equal to 3 over 2. So x equal to 3 over 2. No other possible local extrema. Now, we want to determine if they are indeed local extrema, and we've seen that we can use higher derivatives for this, and of course, if we take a look at this function here, this is again the product of differentiable functions, so it's again differentiable. F prime is again differentiable, and we can again compute the derivative with the product rule. F double prime of x. Now let's use this form here. This is a bit easier to derive. So this is the derivative, first the derivative of this here. This is, wait, something, what did I do? Oh, sorry, I messed up some of the computation. What did I do? This is 3x squared minus, and this is, yeah, I just messed up a sign. This is not 2x minus 3, but 3 minus 2x, very sorry, but the result is the same. This is just changing the sign. So again, x is 0 or x is 3 over 2. I'm very sorry about that. So these are still the two possible solutions of this. So this is differentiable with, and now let's derive first this times that function. So the derivative here is 6x minus, and now 3 times 2x squared. Minus, sorry. So this is the derivative of the first factor times e to the minus 2x. And again, the second part is just minus 2 to the e minus 2x. So this is minus 2, and now the first remains as it was. X squared minus 2x3 e to the minus 2x. Oops, sorry for squeezing. And now this is summarized if we put them together. This is 6x minus 12x squared. I'm just we'll compute this again, plus 4x3 times e to the minus 2x. And this is again rewritten by just, if we just pull an x out of the equation. So we get that f2 of x derived, second derivative of x is x times 6 minus 12x plus 4x squared e to the minus 2x. Okay, this is the second derivative, and here we can see that already the two local extrema, 0 and two possible local extremum points are 0 and 3 over 2, and we can see if we put in 0, because this factor here is 0, everything is 0, so the second derivative is 0, so we can't say anything yet. We have to go further and take more derivatives. But if we take the second derivative at 3 over 2, this is now a long computation, or maybe not that long, I would say, but yeah, anyway, so you can just do, compute this a bit, and you get that this is minus 9 over 2 e to the minus 3, so this is just what you get if you insert everything and compute. And this is the number, of course, this is non-negative, e to the minus 3, because the exponential function of a real number is always non-negative. This is negative, so this is negative. So first thing we can observe, the second derivative here is negative, so it's an even derivative, which is the first non-trivial, non-vanishing. So this means, by Theorem 446, that f has a local maximum in 3/2. And yeah, and the value, and the local maximum is now the value. This is f of 3/2. And this is now you have to insert in there. It's not very nice. It's 27/8, which is just 3/2 to the power of 3, times e to the minus 3. And this value is a local maximum of f. So, considering the graph of f, which I already drew on this next board, if we imagine what f would look like. Okay, we know that here there's some value 3/2. And there it has a local maximum, so let's say it's somewhere here, and this value here is 27/8 times e to the minus 3. And there we know that this points on the graph and that f has a local maximum in there. So it's kind of somehow like this, but we don't know more yet. So the other point in question here is of course 0. So we need to see what happens there. And for this point, so as I said, the second derivative is not enough, so we need to see what's the first non-vanishing one, so we have to compute some more. We can see that f double prime, this is again some polynomial times e, and this is again differentiable. And now the derivative, we even don't need to compute everything. Of course, now it gets messier and messier with the polynomials. So first we can see, let's take where it is, this formulation here. So here it's the easiest to see what the derivative is. First, the derivative of this guy, which is 6 minus 24x plus 12x squared times e to the minus 2x plus 6x minus 12x squared plus 4x to the 3 times minus 2e to the minus x. And I don't care about the precise formulation here. I don't simplify this at this point, because all I need is the derivative at 0. And this I can already read, because many, many things are vanishing if x is equal to 0. For example, this whole summand. And it turns out that f3 at 0 is then 6e to the, to the minus 2 times 0. So here's just a 0, so this is 1. So this is just 6, but the important thing is it's non-zero. So we've seen that the third derivative is the first non-vanishing one, and since 3 is an odd number, we've seen in Theorem 446 that f does not have a local extremum in 0. Okay, and it turns out, if you really draw this graph, that this is, it's kind of a plateau here. So it turns out if you, well, this is now, no, I think it's curvier, something like this. And it turns out that the function is then here, kind of going towards 0, but here it's going to, here it's kind of passing at this point. Oh, it's hard to see, sorry. So nicely. So here we've got the derivative vanishing, the second derivative, but it turns out that here it's going to infinity as well. So this is just some ugly point, but this is not a local maximum and not a local minimum. So this is vaguely what the function looks like. Okay, this concludes chapter 4. We've seen everything about differentiation we kind of need for practical applications so far, and for kind of your, everything you need to know at this point about derivatives. Next chapter will be, and this is the final chapter of the calculus part of this Math 1 lecture, and this is integrals. So we will study integration in detail. See you in the next chapter.